We're on problem 14. And it asks us, what is the solution to the inequality x minus 5 is greater than 14? Well, to do this is just like solving any, equality or equation. What we do to one side, we have to do to the other side. And we want to get rid of this minus 5. And the best way to get rid of a minus 5 is to add 5. So let's add 5 to both sides of this equation. So 5 plus, and then a plus 5. And then a 5 plus a minus 5, that's 0. That's why we added the 5 in the first place. So we're just left with an x on that side. We get x is greater than 14 plus 5, which is 19. And that's choice B. Problem 15. The lengths of the sides of a triangle are. So there we have a triangle. And they tell us the lengths of the sides are y plus 1, and 7 centimeters. They also tell us the perimeter is 56 centimeters. The perimeter is equal to 56 centimeters. What is the value of y? So the perimeter of any shape is just the sum of the sides, right? So y plus 1 plus 7, right? That's the distance around the triangle. And that is equal to the perimeter, which is equal to 56. So let's see, we get y plus y is 2y. Plus 1 plus 7 is 8, is equal to 56. So you get 2y is equal to, what is that, 56. So if we subtract 8 from both sides of this equation, we get, on the left-hand side, we just get 2y. On the right-hand side, 56 minus 8, that's 48. Divide both sides by 2, and you get y is equal to 24. And that is choice A. Problem 16. Problem 16. Now what do they want us to do? All right, I think this is one I should copy and paste. Okay, now they're telling us, let me pick a good color, which number serves as a counterexample to the statement below. So a counterexample, an example that shows that this isn't always true. So the statement is all positive integers are divisible by 2 or 3. So we just have to find a positive integer that is not divisible by 2 or 3, by neither 2 nor 3. Well, 100 is divisible by 2, right? So that just verifies, or it's just another example of a positive integer that's divisible by one of these two. So it's not choice A. It's not a counterexample. 57, it's not divisible by 2, but it is divisible by 3. 19 times 3 is 57. So it's not choice B. 57 is another positive integer that's divisible by 2 or 3. It's divisible by 3, so it's not that. 30 is divisible by both, so that's definitely not a counterexample. But here we have 25. It's a positive integer. And it is neither divisible by 2 nor 3. So it disproves the statement. So it is a counterexample. And so the answer is D. Problem 17. Problem 17. Let me copy and paste this one. Copied it. That's pasted it. All right. What is the conclusion of the statement in the box below? Okay, they say if x squared is equal to 4, so if we know that x squared is equal to 4, then we know, and we know this from algebra, we could have solved it, that x is equal to minus 2 or 2. All right, so what is the conclusion of the statement in the box below? Oh, okay, I think I'm reading this too much. This is the condition, and this is the conclusion. Right? They're saying if this has happened, then we conclude that. So they're actually just asking us to label it. So right, this is the conclusion. Then x is equal to minus 2 or 2. I think that's I don't like that question so much because my reaction was, okay, if this is the whole statement, right? What can I conclude from it? Right? And there's not a lot that I could conclude from it unless they told me that this indeed was true. But anyway, I don't want to get too complicated. They're just saying that if this is true, then we can conclude this. And they're actually just saying, what is the conclusion? So what part of this statement can we label as the conclusion? Well, that's the conclusion, so that's choice D. I didn't like that. That was a little bit more, that was more meaning of words than math. But anyway. Problem 18. All right, let me copy and paste this one too. which of the following is a valid conclusion to the statement? Okay, so now you see if a student is a high school band member, then the student is a good musician. So if you're in the high school band member, then you're going to be a good musician. That's what this says. And if you compare this to the last question, that could be confusing, right? Because a valid conclusion. So once again, here they're giving us a statement. They want us to come to some conclusion. They might have said, "What is the conclusion of this statement?" Right? And then you would have said, "Oh, the student is a good musician." But that's not what they're asking. They're saying, "Okay, if this whole thing is a statement, if we know that this whole thing is true, if they're in the high school band, then they're a good musician," right? Which I kind of wrote in shorthand here. They're asking, okay, if we know that to be true, which of these statements can we conclude from that? Statement A says all good musicians are high school band members. Well, no, that doesn't tell us that. It doesn't say that all good musicians. We could have, the good musicians could be this circle, and the high school band members would be a subset of it, right? High school band, and this could be good musicians. So right, all high school band members are good musicians, but there could be people out here who are good musicians who aren't high school band members. So it's not choice A. A student is a high school band member. Well, no. I mean, high school band members, they didn't tell us that all of the students are high school band members, or the high school band is comprised of all of the students. The student body might be like this circle. Some of them might be in the high school band, some of them aren't and are good musicians, some of them aren't and aren't good musicians. So, you don't know whether someone is a high school band member just by being a student. All students are good musicians. Well, once again, this could be an example. There could be people out here who are students, right? Where that could be the yellow could be students. There could be people who are students who aren't good musicians, right? This statement doesn't in any way constrain that. So let's get rid of that. See, all high school band members are good musicians. Well, let's look at this Venn diagram. That's almost like a restating of what they already told us. All high school band members have to be good musicians because they told us if you're in the high school band, then you're a good musician. So it's almost like repeating the same statement twice, but the answer is D. Problem 19. Problem 19. Let me erase this one. This looks like another one that I'm going to have to copy and paste. Okay. I've copied it. Okay, let me do a dark color. I'll do there. The chart below shows an expression evaluated for 4 different values of x. All right. When x is equal to 1, x squared plus x plus 5, right? 1 plus 1 plus 5 is 7. When x is equal to 2, then 2 squared plus 2 plus 5 is 11. Fair enough. Josiah, or Hosea, I don't know how to pronounce that, concluded that for all positive values of x, x squared plus x plus 5 produces a prime number. Okay? Which value of x serves as an example, serves as a counterexample to prove Josiah's conclusion false? So a counterexample says, he says that whenever I put any positive number here, I get a prime number here, right? And we have to say which one proves him false. If you put 5 there, what is 5 squared is 25 plus 5 plus 5. And what is that equal to? That's equal to 35. So that's a counterexample right there. If x is equal to 5, I produce 35, which is not a prime number. Not prime. Right? So clearly his statement, his conclusion was incorrect. That when you put a positive number here, it doesn't always produce a prime number. That was his conclusion. This one isn't prime. So statement A is a counterexample, or the number 5 is a counterexample here. Next problem, problem 20. Okay, this is one of those where we have to pinpoint the incorrect step. John's solution to an equation is given below. For which step of real numbers which property of real numbers did John use for step 2? Okay, so we don't even have to look at step 1. We just have to say, okay, how did he get from there to there? All right, so to make this, so when you look at this, when you say x plus 2 times x plus 3 is equal to 0, you're saying some number, right? Some number x plus 2 times some other number x plus 3 is equal to 0. So that's like saying, some number times some other number is equal to 0. So that means that one of those numbers or both of them have to be equal to 0, right? Because the only way to get 0 is if one of these or both of these have to be equal to 0. And that's where he gets this conclusion that either x plus 2 has to be 0 or x plus 3 is 0, or they're both 0. So let's see how what do they call it? Multiplication property of equality. I don't even know what that means. Zero property of multiplication. This seems like the closest one for me so far, that anything times 0 is 0. Or if for two things to be multiplied to equal 0, at least one of them has to be 0. And that's what this is right here. Commutative property of multiplication, no, that's not it. Distributive property of multiplication over addition, no, we're not doing anything like that. If we went from this step to that step where we're multiplying it, that might have been because you're really just doing the distributive property, but I don't want to confuse you. Yeah, we're just saying that if two numbers, when you multiply them, equal 0, one of them have to be equal to 0, and I guess the label for that is the zero product property of multiplication. Anyway, see you in the next video.